course is complicated and not everyone understands what it's all about, I will put a record on a YouTube platform. It will be accessible. I'll put direct link to the e-learning system, so you can watch it if you need. Also, I will put test tasks. They are already in e-learning system. For test tasks, to complete course, you need to solve class 4. Link now available on a learning system to this stream. I use YouTube stream because they allow me to put free cameras. This is possible not needed. This is not needed. I can save it. And I can switch to my blackboard. So what we got for today? Theory of signals. What is the course? Why it's here? What are you doing here? It's for it's for electrical engineering. It's the next step or next level after circuit theory. But as I understand, you are not from electrical engineering course. From which course are you? Ah, you're from electrical engineering. 1 second. But from which program? From the adaptronics program. Yeah, from adaptronics program. This means what you do have circuit theory. And you from?
I'm from
Ah, you're on Erasmus one.
Yeah.
From Erasmus student. Okay, but it's general discourses for electrical engineering. It's not for it's like things used. There are some things what are necessary for communication, but we are not interested in them. This course is focused on power engineering and application of this theory in the scope of power engineering. So it's a bit shifted from the classical signals theory towards power engineering problems. Okay, forward. What's forward? What is signal? What I'm talking about here. If you saw the course curriculum, it's a theory of signals. Theory means blah, blah, blah. Something about, but what is signal? Any physical process, I will write multiple times, as function of t. Sorry, my Latvian pronouns. If you don't understand something, raise hand, I will explain. I knew what I'm not the best presenter in this world. So, signal s as a function of t. Any physical value, any physical, what can be physical? Voltage can be, current can be. Students' number at a lecture, also physical. So any physical value observed in time. Signals are determined and stochastic. What means determined? If I have a mass definition for any time moment starting from the world creation and ending at the doomsday, for any time moment, I have exact mass description of my signal. This signal is determined. On the other hand, there are stochastic or probabilistic signals. For such kind of signals, I only knew probabilistic chart or characteristic. So, for example, magnitude of my signal and its probabilistic. Possible value. Distribution. I draw a Gaussian distribution. Here is some kind of maximum value, most probable. In reality, let's take, now camera is recording, microphone is working. Let's take magnitude of sound, the volume. Can we tell what it will be next minute or next 15 minutes? No, you should know what I'm willing to tell, but you don't know. I too. But we can analyze probabilities. Probability 1, doors open, and I say our rector here. Or minister. Education minister here. Silence. Only clocks speaking. It will be lower level, yeah? And what's the higher level? Door opens and bunch of clowns. It will be higher level. So reality will be somewhere between them. We can, of course, we can work with probabilities, but it's not an easy task, and it's not a pleasant task. So usually we try to substitute real probabilistic or stochastic signal with some kind of test signal, some kind of, let's say, ideal representation. But what kind of ideal representation? I work in power system protection. In power system protection, we have a strict rule. If you design a protection device, be so kind and make your device able to withstand 200 amps, if your device is for 5 amp rated current, within 5 seconds. You should be able to withstand possible fault condition. If your device is 1 amp rated, be so kind, but it should, in any case, 40 amps within 5 seconds. So if I take 40 amps as this ideal signal, all real conditions will be met. Yeah? It will be functional in any real condition. So I can do what? I can take most probable, or I can take this substitute, ideal or test signal, substituting real probabilistic in such manner to ensure operation in any possible case. 40 amps, 5 seconds. After that, not my problem. I comply with the regulation. It may be burned. Yeah. So, stochastic and determined. Next important thing. Our life is continuous. So every hour can be split in minutes. Yeah? Every minute in second, and every second in millisecond, and every each millisecond can be split in nanoseconds, and so on. Yeah? Yeah. let's say I have some experiment. I plug an instrument and watch it, my dear friend, and bring me a report. My friend watch, and what I get a report. Time in minutes, voltage in volts. In volts. 1, 2, 3, 4, 5. I don't know. 7, 5, 3, 2. What I got? Time. I don't know. Maybe something like this was original. It's original voltage. But I got a table of measurements. 1, 2, 3, 4, 5, and so on. Let's assume they are spaced equal, but it's not mass. I have a table. And now, question, this table, what it represents? This original white line? No, it's kind of derivative for it. Possibly it wasn't like this, but like this. I don't know, my student don't know, and no one knows. White line is continuous signal, but the set of red dots, what I got as a table, is a discrete time representation of my signal. Why I'm talking about this? Some signals, some dots, some students. Our time is continuous, but computer time is discrete. Digital signal processing system will produce a discrete time representation. Table in the memory. I don't know, it may be large PC, small PC, some kind of embedded device. Anyway, for digital processing system, inner representation of signal will be table, and this table represents signal in discrete time. Measured, unknown, measured, unknown, measured, unknown. Between this measurement nodes or points, value of signal is undefined. Not zero, not something. Undefined, unknown. We don't know it. So its discrete digital representation will be discrete time. Our life is continuous. Digital life is discrete. Next, dichotomy. The name for it is dichotomy. Division. There are periodic and aperiodic signals. If signal repeats itself in a manner equals plus T capital, where T capital is repetition time, it repeats after T capital seconds. Here M is an integer, -1, 0, 1, up to infinity. M is an integer, and this is repetition time of period. Repeating signal. In power engineering, generators are rotating, result is repeating. Periodic signals, sometimes are very handy because to, let's say, analyze network, I need to perform my calculus only for one period. Because they are all the same, results will be the same. In our business, periodic signals, it's something, let's say, quite frequent in our business. Non-periodic or aperiodic signals. Nice example from circuit theory. It's a, let's say, classic. I have a source, I have capacitor, and I have resistance. Here will be output at a time equals to 0. I will turn a switch. What will be output? Time. Voltage is a function of time. 0 before 0 and capacitor discharge where alpha time constant is 1 against C, decaying exponent. It's a continuous signal. It's a determined signal. And it's classics of aperiodic signals. Never repeats. Here I will put a grounding point. Never repeats itself. Okay. Pulse. Another name for such kind of signal, pulse or impulse. Pulse. Pulse. I can do a trick. What kind of trick? Let's say I have this nice network. Capacitance, resistance, here will be ground, here will be my signal. I will take and test signal source producing 1 0 1 0 1 0 sequence and control my switch from it. Let's say it operates with the period of T capital. Okay, it is. Okay, this one is switch and I can do something. Okay, I have it. So what will I get? We will analyze. We will get pulse sequence. Each one is an exponent. But between them is a period defined by switch governor. It's a pulse sequence. Pulse sequence is something what can be analyzed as a periodic signal, but it's an artificial created sequence. Here I have a breakpoint and switch turn. When we will speak on signals, it's good to know some metrics of the signal. Let's say a periodic signal. Repetition time is a period. Frequency in hertz, yeah, inverse of the period. Repetitions per second. Maximum value, yeah, it's an amplitude. Positive, and I can define also amplitude negative. It's minimum value. What else? What kind of metrics I can use? I can rely on average. It's 1 against on time. Average value of the signal. We'll see it later. It's also set, can be understood or set a DC offset. Average value of the signal. Measuring instruments is available, means show us average value. But average value, let's be clear, average value is not so rich in information for us. Another metric of the signal is its effective value. So idea is to compare signal's energy, let's say. It's kind of energy matrix. Idea of effective value, let's say I have my signal, for simplicity I take periodic signal, loaded with active resistance. What we will get? Bit of heat, yeah? So thermal power produced, let's say it's P1. It's a thermal power when my signal is loaded with active resistance. I can take same resistance and connect it to classical DC source. I can, yeah. Also, some amount of heat will be produced. What I can do? I can kind of put them on equilibrium, and if I can tell what my signal is equivalent to this DC source, or DC source is kind of equivalent to my signal, if these thermal powers are equal. So if thermal power are equal, I can say what they are in some kind of equilibrium. And DC source can be used as a kind of metric for my signal. 10 seconds of mass. So So this DC source will be E multiplied by current or E multiplied by E divided by resistance, so it will be E squared divided by resistance. It's very simple. Bit complicated with the first power. In every moment, instant power will be similar S squared time divided by F. Yes? Instant power. We will see. I will show you this instant power. But wait. What will be sum of energy within one period? Within one period, we will get sum of all instant power. So it will be 1 against F, integrating within a period of our signal in time. It's clear. If I, let's say, collect all instant powers, I will get whole energy counted on matter within one period. Yeah? Who prevents me from connecting signal to matter? Now, what is watt? We measure power in watts. Yeah? Watts, megawatts, kilowatts. What's a watt? 1 joule within 1 second. This means what vector can be taken if we divide energy within period by time of this period. It will be measured here. Wattmeter hiding. I will not use this transformer today. So I can write a simple equation. E squared divided by F equals to 1 against Tn from 0 to time S squared. Or finalizing, it will be square root 1 divided by period. I should take an integral from 0 to time. Here it is. It's an energy, let's say energy matrix or kind of energy value of my signal. DC source what will produce the same amount of power as my signal. It has a name of a signal effective value or RMS, because root means square. RMS. Each time you take a measurement instrument and see something like RMS or TRMS, true RMS, it's an instrument showing you this nice value. So it's a DC equivalent of signal measure. Effective value. Good to know it when you ask, what will be payment for this? What will be my bill? It gives you energy. And you pay for watt hour, kilowatt hour, megawatt hour, and so on. Okay, these are some signal metrics. One more moment. In ideal world of power engineering, we deal with signal kind cosine time, or some kind of marks, sine omega time, something like this. Such kind of signals are called harmonic signals, because ideal pure sound tone described like this. One nice differential equation describing oscillation has solution like this. For such kind of signal, RMS will be S max divided by square root of 2. You can check it. Okay, that's nice. But I want more. I would like to go a bit further. Oh. I'm changing frequency, isn't it? And I can change amplitude. But can I see this signal? Can I get it visible? Not to hear, but to see. Not hearable, but visible. Ah, nice question, isn't it? Sweet. I'll start with old technology. Here I have one of the demo. Professor Crookes sometimes created a set of physics demonstration. This is one of them. They call Crookes tubes or Crookes swamps, often Crookes tubes. This is one of them. What's the idea of this demonstration? I have kind of vessel with pair of electrodes, HT. High tension or high voltage source should be connected. If voltage is high enough, electron can lift this surface of this disk. If voltage will be high enough, energy supplied to one electron, one particular electron, will be higher than the job needed to lift the metal surface, and our electron will fly freely to the opposite electron. Here in blue flies electron. Crookes put a disk with the slot. Here it is. In the I should better draw it like this. Disk with the slot is here. To create a kind of flat beam of electrons. And on the way of this beam, this nice screen is placed. This screen is covered with the zinc sulfide. The good thing about this zinc sulfide, it goes. When it's a subject of electron flow, it produces visible green light. It's not very strong, but visible. One second. Oh, here it is. One moment, I need to adjust my camera. Yeah. Here it is. Nice beam of electrons. Flow of electrons is a current. If I put current in magnetic field, force, ampere force. So in magnetic field, electron beam is deflected. You can see. It's the way old TV set worked. They had a set of coil. Here it is. Nice physics demo, isn't it? But that's not all. You can see Crookes' design also incorporates two disks, these two surfaces. I would like to connect wires to them. This goes here, and crankshaft generator comes here. What's the idea? Let's say I have these two surfaces. And let's say I put a positive charge here. This means on the opposite side will be negative charge. Physics teaches us what electron has a negative charge, even measured. If something is charged negative, positive charge attracts it, negative pushes away. Yeah? That means what electron beam should be deflected up. In opposite case, if I put a positive charge here, it should go down. Yeah? Let's see. Let's see what happens. Can you see? Yeah. It follows. Okay, it should go slow. Beam follows generator. I can control electron beam, and it's something that has very low inertia, isn't it? Yeah. Where is my CFD? Here the idea for oscilloscopy. Cathode ray tube. This part produces beam of electrons. Here you can see deflection plates. You see them? Again. here at the flat plate, and surface covered with same zinc sulfur. Maybe I should draw it.
Excuse me. Excuse me. What is the name of this machine?
This one.
No, just next to. Just near on the
The
left.
one with the range when you saw them.
Yeah. We have our experience.
Which is
The
it?
cathode.
No, it's the left. It's the left.
The left.
Just
That one,
yeah.
yeah.
This one is Crux. The name. Crux tube
Thank you.
machine. It's a demo device. Crux tube. And this oversized Western Electric dynamic special series for physics. As I learned. So let's say we have something like this. We will need a heated cathode, usually it's 6.3 volts. It's easier to electrons to left a heated object. Modulator. Thin electron beam will left. It also can have a focus ring. It's not important. Important. Set two sets of plates. Something like forming something like this. It's x1, x2, y1, y2. Avoid this and this. Something like this. Set of plates. If they are not so articulated, I have this beauty. It has memory. Case one set of plates, and the second one here. And this nice device produces an electron beam and a screen. Plastering and surface covered with luminescent zinc sulfur. I will have two channels, X and Y, vertical and horizontal. Now my generator here is connected to the horizontal one. I'll bring camera closer. Here it is. Low frequency. Make it clear. You can see beam going. Yeah, that's better. It is going left, right, left, right. Up and down, up and down. Y channel is activated. If I have two channels, why I am using only one source? 1 second, I will bring the second one. Is my generator number 2. Show here. The bigger one is on the vertical channel, and smaller one is horizontal. One moment, I'll set something. Here I have 400 Hertz. I will adjust to use offset voltage. Here it is. At this moment I have two signal from the smaller on a horizontal movement and signal from the larger on the vertical. Lissajou figure of Lissajou. Results of two signal guiding this electron beam simultaneously. Now they have near, if it would be ideal, equal frequency. Figure, I can try to hold. Yeah, now frequencies are equal. 0.5% difference in one direction, 0.5% in opposite. Let's see what I can do. For example, (800 Hertz on the vertical channel and 400 on X on horizontal. Nice research figure. Or 1000 Hertz, 1 kilohertz on vertical, and still 800 on horizontal. Research figure. Maybe something like 500 and 200 and 400, sorry. Lower. And this one will be steady. 200 Hertz on vertical channel and 400 on rotates. Appears to rotate in vertical around the cross. Here it is, with a figure. Little stars of the physics demo. Now, what do we see in reality? Bunch of green dots. What's rotating? You see it rotating? It's just two harmonic signals. If we draw a chart, we will have x, y, and some line y as a function of x. Yes? What's here? We have horizontal x, we have vertical y. What's the horizontal? Cable, 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 cable leads us to the small generator. So here we have signal number 1. Yeah? What's here? Signal number 2. And line is not as a function of signal 1. We have something. It's an example of functional representation. Second signal drawn as a function of the first signal. It's an analysis tool. What should we do if we would like to see signal as a function of time? First signal should be proportional to time. Yeah? Use a signal like this, proportional to time, and you will get you will get this. You will see your signal as a function of time. But it runs. You see with the purples. It runs. It's not, picture is not steady. Because there is a frequency shift between KT voltage or so voltage enter my signal. So synchronicity circuit should be added. Time observable, let's say, as time. You need an internal like 0 or AS voltage. It should trigger timing at the cross points. 1 second, I will activate it. I'm changing this voltage. Positive one. See, it switched the 0 time. It changed, not switched, but changed the 0 time. Sorry. Here. Positive, negative. It changes the 0 time of my scope. So here is the way analog scopes work. Who needs analog scopes? Sometimes they are needed. On the modern digital scope, research figures are not so aesthetic. What I got for 400. And let's say 800 on vertical and 400 on horizontal. Nice research figure. Idea of research figure is basically it's an idea what one signal can be represented as a function of another. That's why I'm talking about it. Okay. We have one viewer on line. Maybe some questions? Oh no, mistake. Maybe my online viewer would ask some question. Research figure turns. Okay, I need not what I need to do. I need to fill attendance chart. Machine don't like me. This machine don't like me. And what's this? Something wrong. 100%. I need this one. I need this one. What is... I will fix it. Everything can be fixed. Where is my attendance chart? Today. Oh yeah, appeared. Yes. It worked. That's nice. I have problem with previous. Should so. Okay. I need to fill attendance chart. Can you show me your name? Seriously, I hate dislike people, dispel people. Can you point a finger on the screen? Real. I hate misspell people's name. Where should I put a mark?
Up. Same. Nante.
Yeah.
And this six.
Oh yeah. And where is create? See the problem. For in some cultures, shoe name is the last one, and some is the first one. I hate misspelling. Yeah. Here it is. Okay, but why? Okay, it's from out of the whole group. For some reason they shifted time. But it's next week. It's no, not after next week. It's 17. No, I'm just blaming the system. Don't worry. Okay. What shall we do? Where shall we run? What I need some. Because time left, this means that I forgot something. Rotate. Okay. And now please go opposite way. It rotates with the frequency equal to the frequency difference between generators. What I forgot? Something. Show a bigger picture of my setup. Yeah. X-axis generator, Y-axis generator, and scope with research figure. 20 minutes. Okay, I took 10. I have still 10 minutes. It's only 10 minutes. What I forgot to tell. There should be something. Okay. If I don't remember, maybe it's not important. Some questions online? Last chance to ask a question. Maybe you have some question. It's lot of. Look, I just started. There will be much more. Actually, what I did. If you're a learning system, you can see records from the previous year. You can follow, for example, some students are following dynamics of garbage in this corner. Others may follow dynamics. How pile of garbage grows. 2 years ago there was nothing. Then ammeter took his place, and receiver. And for demos of asymmetrical network, I bring this motor in. Garbage piles. But it's not. Maybe this motor will help us, and maybe smaller one. I have a lot of